As we mentioned before, a loop arrangement is generally employed in sub-transmission systems and even in the distribution system on occasion. In its simplest form, there is only one source of supply, and the loop is often split, usually at the far end. In this case, we have effectively two separate radial circuits, and the protection coordination will be similar to that which we have just looked at in the previous segment. However, in order to provide increased reliability, the loop may be operated fully connected so that current flows in either direction around the loop, depending upon the magnitude of the load at different locations. In a sub-transmission loop, breakers will be located at both ends of each section of line feeding into the various buses. Now, if a fault were to occur, say, at the very end of the loop, at this point, current flows from the source to the fault in a clockwise direction along the upper part of the loop, and in a counterclockwise direction along the bottom portion. The overcurrent relays are set up to be directional with the tripping direction looking into the line. For example, for these breakers, 3, 4, 5, and 6, the directional element will trip in a clockwise direction. At breaker number 2, there will be no need for directional control, as fault current will always flow in one direction only. Similarly, breaker A does not need directional control. However, breakers B, C, D, and E need to be set up with their directional control in the counterclockwise direction. The coordination of the relays must be performed in two stages. That is, first the clockwise loop, and then the counterclockwise loop. For the sake of clarity, we can lay out the clockwise group of breakers in a line like this, starting at breaker 2 and working our way through breakers 3, 4, 5, and 6. For this part of the study, breaker A is assumed to be open. The coordination curves of the time overcurrent relays are shown here. The fastest operation is breaker number 6. As we approach the power source, each relay would be set up with a longer time delay so as to allow the farthest relay to operate first and clear its faulty section of line. For example, look at a fault at the end of the line. If breaker 6 fails to open, then the relay at this bus location will open breaker 5 after the additional time delay. This time interval between relays at each specific location is known as the coordinating time interval. Generally speaking, the coordinated time interval is set to 0.2 to 0.3 seconds. The minimum pickup of the relay is set, as pointed out in the last segment, at 1.5 to 2 times the short-term maximum load at that part of the circuit. Once the coordinated settings of the clockwise group of relays have been completed, the exercise must now be repeated for the counterclockwise loop. In our example, this would be breakers A, B, C, D, and E, assuming that breaker 2 is open. Both sets of coordination curves can be shown on the line diagram like this. The upper group refers to the clockwise loop and vice versa. Finally, operation of the whole protective scheme should be checked by assuming various fault conditions. This would include all breakers closed on the loop and the application one at a time of a fault at each end of each section of line. The calculated values of fault currents should be used for both maximum and minimum operating conditions. This study may bring to light certain minimum conditions that perhaps do not operate the relays as desired, thereby necessitating a re-examination of the relay settings. Another potential problem is a backup relay that operates too soon and therefore trips out a larger section of the line than would be necessary to clear the fault. To overcome this problem, it may be necessary to slow down the operation of overcurrent relays close to the power source in order to provide the required coordinating time interval. But this means the relay may be too slow to adequately clear close-in faults in its own section of line. The best method of resolving this problem is to install an instantaneous relay set to reach about 70% along its section of line. This means it will trip the breaker instantaneously for line faults which occur up to this point, but it will not operate for faults at the end of the line. We certainly do not want it to overreach and trip for faults in the next section of line. This would cause complete miscoordination. Setting of the instantaneous relay is complicated by the high transient current which exists at fault inception and is determined by the system's X/R ratio. At the instant the fault occurs, the relay may see up to the square root of 3 times more current. In practice, the relay setting is increased so that the relay's instantaneous unit will not overreach its intended set point. For example, on 345 kV applications, the setting is increased by up to 1.5 times. Looking along the line, the set of coordination curves would look like this, where instantaneous overcurrent relays are installed in addition to time overcurrent relays. Clearly, the biggest improvement in relay operation is close in to the power source. The reduction in time for a fault at this location is significant. There is another incidental advantage. The upstream time overcurrent relays can now be coordinated with the downstream instantaneous relays. Thus, the new coordinating time interval is this distance here. So the time curves can be lowered with lower time dial settings, thus reducing tripping times. Where the loop has several sources of power supply, the problem of coordination of overcurrent relays becomes far greater. Particularly problematical is the difference in conditions between maximum and minimum load periods. For example, during minimum load, some of the power sources may be completely disconnected, and this will probably bring about a complete change in direction and magnitude of flow of fault current. For complex systems, such as found on transmission networks, the overcurrent relay is really not adequate, and other types of protection are used, such as distance relays. One definite limitation of the overcurrent relay is that it is sensitive only to current and does not respond to other parameters such as voltage, for example. But as we know, in case of a severe fault close to the power source, quite often the voltage falls to a very low level. As a result, the level of fault current may be below the pickup setting of the overcurrent relays. One type of overcurrent relay, the voltage restrained or voltage controlled relay, does take account of voltage as well as current. Depending upon fault calculations, the pickup of this relay is often set to a current level which is actually below normal maximum load current for the circuit. As long as voltage is normal, the relay will be restrained from operation. However, if the voltage falls to a predetermined level, say 70%, the restraint is lifted and the overcurrent element is released for operation. Please switch off the tape and review this material in your